Hello, this is John Miares, and in this lesson, we are going to go back to section 1.9 of the textbook to review equations of circles. This is the first of a series of video lectures I am creating with the idea that most of the new material will be covered here, and any big questions or review will be covered during the online real-time session. To that end, the hope is that you are watching this video prior to the online real-time class where we will be going over this material, so that you will be prepared to discuss it and ask appropriate questions. Once you've completed watching this video, you should try to do the problem challenge problems listed at the end of the slideshow on your own. We will be going over the problem challenge problems during the online real-time session. And I'll also try to answer any other questions that you might have posted on the discussion board on this topic. Now, there is a notes packet on D2L which corresponds to these slides. One thing you wish to consider is taking notes from these slides in that notes packet as if you were following the presentation in a live face-to-face setting. Of course, if that doesn't work for your learning style, you can always review this video later if you have questions, or you can look at the slides by themselves, which will be posted in the Week 1 folder in the D2L content area. What I would recommend, however, is if you want to look at these slides later, that you download them from D2L to your own device and run them from there so that you can follow the animations that have been built into each slide. If you review the slides using the D2L previewer, none of the animation or dynamics in the presentation will come through properly. With that, let's get started. You've probably been working with circles since you were very young, and many people, when asked what a circle is, will probably talk about a shape that is round with no straight edges, no sharp corners, no starting point or ending point, and it has something to do with pi. Well, in mathematics, we have a more formal definition of a circle. Now, a circle is a set of all points in a plane, which is a flat two-dimensional surface, that are a fixed distance from a fixed point known as the center. The distance from the center point to any point on the circle is called the radius, and the diameter is the segment that connects the 2 points on the circle through the center point. Here we have a diagram showing the circle, marking the radius, the diameter, the center, and the circumference. The distance from the center point to any point on the circle is called the radius, and the diameter is the segment that connects 2 points on the circle through the center point. The length of the diameter is 2 times the radius. The distance traveled by following the arc of the circle all the way around is referred to as the circumference of the circle. And the length of the circumference can be calculated by multiplying the diameter, or 2 times the radius, by the number pi, which is an irrational number approximated by 3.14159. Now, back in Math 121, you hopefully covered graphing of circles, so hopefully this is all a review to you. For circles to be plotted in the Cartesian coordinate plane, also known as the rectangular coordinate plane or the xy plane, the standard equation of a circle with center point hk and radius r is given by this equation: the quantity x minus h squared plus the quantity y minus k squared equals r squared. So, clarifying, the values of x and y are here represent the coordinates of any point on the circle itself. H and k are the coordinates of the center, and r is the radius. The main idea behind this equation is that we're looking at the distance formula, or more similarly, the Pythagorean theorem, and computing the distance between the arbitrary point xy and the fixed center point hk. If we look at the base, the horizontal distance can be measured as x minus h, and the vertical distance can be measured as y minus k. This will create a right triangle with hypotenuse r. Applying the Pythagorean theorem, which we normally know as a squared plus b squared equals c squared, by labeling a equals x minus h, b equals y minus k, and c equals r, This quickly simplifies from a squared plus b squared equals c squared to the equation we see for the circle here of x minus h all squared plus y minus k all squared equals r squared. Here's the first example. Find the equation of a circle with center point at -2, 3 with radius 5. The first step in finding the equation of this circle is to write down the general equation in standard form. X minus h all squared plus y minus k all squared equals r squared. From there, I'm told that the center, hk, is -2, 3. That was a given. I also know that the radius is 5 because that was given. So r squared is 25. Plugging those values in for h, k, and r, remember we're subtracting -2 from x, then subtracting 3 from y, will simplify to give a final answer of x plus 2 quantity squared plus y minus 3 quantity squared equals 25. Now, before we do the next example, I'd like to look at the graph of this circle. If I'm doing this freehand, the first thing we'll need to do is plot the point -2, 3, which is our center. Since the radius of the circle is 5, then all points that are on the circle will be 5 units away from the center. Of course, there's an infinite number of points, so we're going to find the 4 easiest to work with, which will be a point 5 units to the right and 5 units to the left, then 5 units up, then 5 units down from the center point. I have those labeled here as the points 3, 3, -7, 3, -2, 8, and -2, -2. Once we have those 4 points in place, we can either do our best to draw the circle freehand through those 4 points, or we can use a compass. Here, I'm using the program Desmos to generate this graph. And what I notice in Desmos is that there are other points that have been identified as also being on the circle, including 2, 0, 2, 6, -6, 6, and -6, 0. How can we verify this? Well, you should recall from Math 121 and earlier courses that every point on a graph has to be a solution to the equation for that graph. This is something I often refer to as the golden rule of graphing. Simply stated, as every point on a graph is a solution to the equation for a graph. What that means in context is that if I want to verify that the point 2, 6 is on the circle, all I have to do is plug in the values x equals 2 and y equals 6 into the equation to see what I come up with. As you can see here, when we do this, you get 2 plus 2 equals 4, squared is 16, and 6 minus 3 equals 3, squared is 9. That adds up to 25. Similarly, to verify the point -6, 0 is on the graph of the circle, we can plug in x equals 6 and y equals 0 into the equation and get -6 plus 2, which is -4, squared is 16, plus 0 minus 3, which is -3, squared is 9, which adds up again to 25. I won't show this for the other points, but rest assured it will hold true for all the points that are marked on the circle. So here's our second example. Find the equation of a circle whose diameter has endpoints at -1, 3 and 7, -5. In this case, I probably want to draw a picture of this first because in order to find the equation of the circle, I need to know both the center point and the radius, and I don't know either one. So first I'll get out a graph and I'll plot the two endpoints of the circle at -1, 3 and 7, -5. Then I will connect the 2 points with a line segment like so. The center of the circle will be the midpoint between the two ends of the diameter. Now, while there is a midpoint formula that you can refer to in the textbook, This is one where I'm just going to use intuition to find the midpoint. Knowing its coordinates will be halfway between the two x values and halfway between the two y values. In fact, the midpoint formula says we should be taking the average of the two x's and the average of the two y's. This will give us the point 3, -1. From here, having a center and diameter, I'm going to draw out this circle. So now we know what it looks like, we need to find its equation. We know there is a center point that has to be labeled as HK. So that's going to be the point 3, -1. So H equals 3 and K equals -1. Now from here, we actually have two ways to find R or R squared. We can use the distance formula to compute the radius of the circle, or either the distance from the center to the given point, or you can even use the distance formula to calculate the length of the diameter and cut that value in half to get the radius. Here, I'm going to take a different approach by applying the golden rule of graphing I discussed on the last slide. I know the center is 3, -1, and I'm given two different points on the circle. The golden rule of graphing says that every point on the graph is a solution to the equation. So I'm going to plug in x equals 7 and y equals -5 into the standard form of the equation, along with h equals 3 and y equals -1, and use that to solve for r squared value. Here we see 7 minus 3 is 4, squared is 16, and -5 minus -1 is -4, squared is 16 again. Adding these together gives us 32. So r squared is 32. If we were asked for the radius, we would simply simplify that as the square root of 32, or 4 square roots of 2. But what we're asked for is the equation of the circle, which will be given as x minus 3 quantity squared plus y plus 1 quantity squared equals 32. In this example, we're going to work backwards, where we are given the equation of the circle and asked to find the center and radius. In this particular problem, the equation is already given in standard form, x minus 3 quantity squared plus y plus 2 quantity squared equals 25. Considering the standard form, the values of h and k, which determine the coordinates of the center point, are subtracted from h and k inside those parentheses, giving h equals 3 and k equals -2. So your center point is 3, -2. The radius is the square root of the r squared value on the right side of the equation. So the square root of 25 is 5, so the radius of this circle is 5. We're also asked to sketch this graph, so I'm going to show this out step by step again. First, we must plot the center point at the coordinates 3, -2. From there, I'm going to plot 4 key points. First, I'm going to go right 5 and left 5 to get the points 8, -2 and -2, -2. Then I will go up 5 and down 5 from the center point to get the points 3, 3 and 3, -7. From there, I will draw my circle through those key points. Now, this example is very similar in that we are given the equation of the circle and asked to find the center and radius, but here there is apparently nothing being subtracted from the x and the y terms being squared. Based on this, we're going to conclude that the center is 0, 0, because I can think of this as x minus 0 squared and y minus 0 squared. The radius is going to be the square root of the r squared value on the right side of the equation. So the square root of 16 is 4. And so the radius of the circle is going to be 4. To sketch this graph, just like before, we must plot the center point at the coordinates 0, 0. From there, we plot 4 key points that are going to be 4 units away from the center. First, I'm going to go right 4 and left 4 to get the points 4, 0 and negative 4, 0. Then I will go up 4 and down 4 to get the points 0, 4 and 0, negative 4. And from there, draw my circle through those key points. So now things get a little bit tougher, but hey, you're in college now, you're tough. We want to find the center and radius of the circle given and then sketch its graph like before, but unlike before, we are not given the equation in standard form. What it looks like is that it is an expanded form where all the individual terms have been squared out or FOILed out so that the center and radius cannot be quickly identified. The next few slides are going to show how we're going to convert this equation into standard form using a process called completing the square. The first step in completing the square for both the x and y terms is that we need to rearrange the terms to group the x's and y's together. Then we want to leave some space after the x term and after the y term to insert a constant. So here we have the equation x squared plus y squared minus 4x plus 2y equals 4. Using commutativity, we're going to rearrange and group the x terms next to each other and the y terms next to each other. So we have x squared minus 4x plus y squared plus 2y equals 4. Then I want to separate out and provide some space after the middle x term and after the middle y term to insert some constants that we're going to use to factor this expression into two perfect trinomial squares. Step 2, we're going to look at the x values and determine the constant that would be needed to have a perfect trinomial square for x. A perfect trinomial square is a trinomial where when you factor the expression to get two equal binomials being multiplied, or rather a binomial being squared. If you recall from your factoring experiences from previous courses and an understanding of the FOIL method, to figure out the correct constant term, take the coefficient of the middle term, cut it in half, and square it. This process will work as long as the lead coefficient, that is the coefficient of the x squared term in this case, is 1. In this case, the middle term is negative 4x, so half of negative 4 is negative 2, and negative 2 squared is 4. So I'm going to insert a plus 4 next to the minus 4x term. To keep the equation balanced, which is a requirement in this process, we're also going to add 4 to the other side of the equation. Next, we want to do the same thing for the y's. The coefficient of the y term is 2. Half of 2 is 1. 1 squared is 1. So we're going to add 1 to both sides of the equation, and we now have this set up as x squared minus 4x plus 4 plus y squared plus 2y plus 1 equals 4 plus 4 plus 1. Step 4, we're going to factor the two trinomials into perfect squares and simplify the constant on the right. Let me move some stuff out of the way to make room for what we're doing here. All right, that's better. Now, factoring the x's and the y's separately using the AC method or whatever method you prefer to factor the expressions will give us x minus 2 quantity squared plus y plus 1 quantity squared. Then simplifying the 4 plus 4 plus 1 gives 9. So now we have our equation in standard form. X minus 2 quantity squared plus y plus 1 quantity squared equals 9. Now we're ready to answer the original question, which was to find the center and radius of the circle and sketch the graph. Now that it's in standard form, we can readily identify the center point as 3, negative 1, and the radius as the square root of 9, which is 3. To sketch this graph, just like before, we must plot the center point at the coordinates 2, -1. From there, we plot 4 key points, just like before, that are going to be 3 units away from the center. First, we go right 3 and left 3 to get the points 5, -1, and -1, -1. Then we'll go up 3 and down 3 to get the points 2, 2, and 2, -4. And from there, we can draw the circle through those key points. So here's the last example, and it's pretty similar to the one we just did. Find the center and radius of the circle with the given equation and sketch its graph. The strategy is exactly the same in that we're going to complete the square for both x and y, but I'm going to recommend that you pause this video and try this one out on your own before you see the answer on the next slide. As a reminder, you'll want to regroup the terms to put the x's and y's together and leave space to insert constants. Then we'll determine the constants necessary to complete the squares for x and y, which, since the coefficients of the squared terms are both equal to 1, the constant you'll want to add will be half the coefficient of the middle term squared. Now, I mentioned the lead coefficient because in the next section, that will become an issue. From there, we'll add the constants to both sides, factor the trinomials, and simplify the equation into standard form. Then, we'll answer the question about the center and the radius. I'm going to recommend you pause this video for a couple of minutes to try this one on your own, and then we'll go over the solution on the next slide. So here we are. The first thing we need to do is regroup the terms to get the x's together and the y's together. And I'll move that -19 to the other side so to just get it out of the way. So it looks like x squared minus 8x plus y squared minus 2y equals 19. Looking at the x terms, half of -8 is -4, and -4 squared is 16, so I'll add 16 on both sides. For the y's, half of -2 is -1, and -1 squared is 1, so I'll add 1 to both sides. On the right, we have 19 plus 16 plus 1, which is 36. And on the left, we can factor those expressions into the terms x minus 4 quantity squared plus y minus 1 quantity squared. Now that we have this equation in standard form, we can see that the center is going to be 4, 1, and the radius is going to be the square root of 36, which is 6. Now, one quick note I want to make. So far, most of the problems that we've had have shown in these examples had radiuses or radii that have been whole numbers and r squared values that have always been perfect squares. That's not always going to happen here. There will be times when the r squared value will not be a perfect square, so your radius will be irrational, and you might need to apply your skills in simplifying radicals. Well, that's just the way it is. Well, now to sketch this graph. Just like before, we must plot the center point at the coordinates 4, 1. From there, we'll plot the 4 points that are going to be 6 units away from the center. We'll go right 6 and left 6 to get to the points 10, 1 and -2, 1. Then I'll go up 6 and down 6 to get to the points 4, 7 and 4, -5. Finally, with those points, we can draw the circle. So that is my presentation on circles from section 1.9. Hopefully, this was review for most of you. Here are some problems from the textbook for you to practice on your own that we will be discussing in class during our online real-time session. Although these problems will not be graded, they are very similar to problems you will see on the WebAssign homework and are typical of the types of problems that you should know how to do in preparation for our first quest. In fact, if you can do the problems from the problem challenge, you should be okay with these types of problems on the quest. The answers to these particular problems should all be available in the back of your textbook, or for those of you with an ebook, there's probably a resource near the very end of the book that has the answers to the odd numbered problems. Of course, if you do come up with questions about this material that you would like to pose before our next class, remember you can either email them to me at miaresj@d2l.lcc.edu, or you can post them to the discussion board under the general questions and items to share forum. Thanks for watching, and we'll see you all soon.